Increasing model size and training computation does not repair missing, repeated, or misleading data. I'm Mehrdad. In this lesson, we will follow text from collection into pre-training, balance model size with training tokens, and include future serving cost in that decision. We will also explain continued pre-training, synthetic data benefits, and how repeated synthetic-only training can erase rare examples. Suppose a team trains a large model with an expensive cluster and reports a strong average training loss. The deployed model still misunderstands domain terminology, invents references, and performs poorly on the application's documents. Another problem appears during evaluation. Some test questions were copied into the training collection, so the reported score is higher than performance on new examples. Additional computation makes the model learn the supplied data more thoroughly. It cannot add a missing domain, correct an unbalanced source mixture, or make a contaminated evaluation trustworthy. Before increasing model size or training duration, inspect which sources enter the dataset, how often each source appears, and which examples must remain outside training. Scaling decisions begin with the data the model is allowed to learn. If this explanation is useful, like the video and subscribe to follow the series. Pre-training uses next token prediction over a very large collection of text, code, and other supported data. Building that collection requires several decisions before training begins. Collection gathers documents from approved sources. Filtering removes corrupt, unsafe, low-quality, or unwanted material according to defined rules. Deduplication detects repeated documents or passages, so the model does not see the same content far more often than intended. Data mixing controls the share of code, conversation, science, news, and other domains. Decontamination compares training examples with evaluation sets and removes matches that could make test scores reflect memorization. Each stage changes model behavior. Aggressive filtering may improve average quality while removing minority languages or rare technical content. Deduplication reduces repetition but can also reduce legitimate variations. A poorly chosen mixture can leave an important domain underrepresented even when the total dataset is enormous. Record the source, license, filtering decision, and mixture share for each dataset component. When a model report says it used high-quality tokens, look for the operational definition of quality and the evidence that important coverage remained. A fixed training budget can be divided between a larger model and more training tokens. A model with more parameters can represent more complex patterns, but those parameters require enough examples and optimization steps to be learned effectively. A smaller model, trained on too many tokens, may lack the capacity to use all of the available structure. Compute optimal scaling searches for the model size and token count that produce the lowest training loss within a fixed amount of computation. The main result is that model size and training data should usually grow together as the budget increases. This principle is often associated with the chinchilla scaling study. Do not turn it into one universal number of tokens per parameter. The fitted relationship changes with architecture, data quality, tokenizer, optimization, and the range of models included in the study. Use scaling experiments from your own model family when possible. The practical lesson is stable. Compare joint changes in parameter count and training tokens instead of increasing only one quantity. The best choice for one training run may not minimize the total cost of using the model afterward. A smaller model usually needs less memory and computation for each generated token. Training that smaller model on additional data may improve its quality while preserving the lower serving cost. This approach spends more computation before deployment so that millions of later requests become cheaper. Several recent model reports describe smaller or medium-sized models trained on tens of trillions of tokens. Those reports show that long training is practical at large scale, but they do not establish one token count that every model should copy. Estimate how many requests the model will serve, the average input and output length, the required latency, and the expected operating lifetime. Then compare the added training cost with the repeated serving savings. Training beyond the point chosen by a simple training loss calculation is often called overtraining. When the choice is made to reduce lifetime inference cost, it is called serve optimal training. The word overtraining here describes additional useful training, not memorizing the training set until quality degrades. Before selecting model size and token count, define which cost or limitation matters most. The first objective is the lowest training loss under a fixed training budget. This is train optimal scaling. The second objective includes the cost of every future request, as well as the original training run. This is serve optimal scaling, and high request volume can favor a smaller model trained for longer. The third limitation is data quality and coverage. No allocation of parameters and computation can teach a domain that is absent or make duplicated low-quality text informative. Considering training and future inference together is sometimes called inference-aware scaling. The term is less important than the calculation. Estimate training computation once, serving computation per request, expected request count, memory requirements, and task quality. A research experiment used briefly may prioritize the first objective. A widely deployed product may prioritize the second. Both fail when the dataset does not contain reliable examples of the required behavior. State the objective before comparing your token count with another model report. A general base model may have limited exposure to legal records, medical notes, scientific papers, or another specialized domain. Continued pre-training keeps the next token prediction objective, but changes the data mixture toward that domain. The model updates its weights by reading substantially more domain text, which can improve terminology, document structure, and factual patterns before task-specific instruction training begins. This stage is also called domain adaptive pre-training. Instruction tuning solves a different problem. It teaches the model how to respond to demonstrations and requests, but a small instruction dataset may not provide enough text to build broad domain knowledge. A common sequence begins with the general base model, continues pre-training on domain data, and then applies supervised instruction tuning and any later preference training. This order is not mandatory. Continued pre-training can also damage general capabilities if the domain mixture is too narrow or the learning rate is poorly chosen. Evaluate both domain tasks and general tasks after the adaptation stage. Use continued pre-training when the missing behavior comes from insufficient domain exposure, not merely from an unclear response format. Synthetic data can add examples when real data is scarce, expensive, or difficult to explain clearly. A strong model can generate worked solutions, rephrase existing text, or create variations that improve coverage for a smaller model. The risk depends on how synthetic data enters later training rounds. In a replacement loop, a new model trains mostly on outputs generated by the previous model instead of retaining the original real examples. Common patterns survive because the generator produces them frequently. Rare events, unusual wording, and edge cases appear less often and may disappear over repeated generations. This progressive loss of the original data distribution is called model collapse. An accumulation process keeps the real data and adds synthetic examples rather than replacing the source collection. Retaining real examples can reduce collapse under some training assumptions, but accumulation is not an automatic guarantee. Low-quality synthetic text can still dominate the mixture, repeat errors, or overwhelm rare real examples. Track the origin of every example, limit synthetic shares by data type, preserve high-value rare cases, and evaluate distribution coverage across training rounds. Ask whether synthetic data is expanding the real dataset or gradually substituting for it. Scaling laws describe measured relationships between model size, training data, computation, and outcomes, such as training loss. They do not guarantee safe behavior, correct tool use, factual answers, or success on every domain. Evaluation contamination creates another risk. If a benchmark example or close copy appears in training, the model may reproduce the answer without learning a rule that generalizes. Keep evaluation sets and their near duplicates out of the training collection whenever possible. Use private or newly created tests for important product behaviors, and document when contamination cannot be ruled out. Safety and tool evaluations should reproduce the permissions, context lengths, and output formats used in deployment. A larger training run may improve average capability while leaving a specific policy or tool failure unchanged. Treat scaling predictions as planning evidence within their measured conditions. Release decisions still require evaluations that match the model's actual users, risks, and interfaces. Remember 3 ideas from this lesson. The data pipeline determines which patterns the model can learn. So collection, filtering, deduplication, mixing, and decontamination are part of model design. The best model size and token count depend on whether you optimize one training run or the lifetime cost of serving many requests. Synthetic data can expand coverage, but repeated replacement of real data can remove rare examples and cause model collapse. In video 16, we will examine how parallelism, flash attention, and numeric precision make a selected training run execute efficiently across hardware. I'm Mehrdad, and I'll see you in the next video.